Okay, so today we're going to introduce in a little bit more detail the last concept in terms of Newton's laws, at least just strictly Newton's laws by itself. And that is diving into a little bit more about friction. Okay? Now, friction, by its textbook definition, is a retarding force that resists an object's motion, meaning it's just simply always going to try to work against an object's motion. Now, friction is dependent on two factors. It is dependent on the object's weight. You want to think of it this way, the friction between two surfaces. Okay? If an object has more weight, it's going to press those two surfaces together more. Okay? That is going to increase the amount of friction that you are going to encounter. And it also depends on the types of surfaces that are coming in contact with each other. Okay? If you have very smooth surfaces, they're not going to have a whole lot of friction as they try to slide past each other. Okay? One of the biggest misconceptions about friction is that some people wrongly believe that the amount of surface area that comes in contact with whatever it's sliding on is going to provide more friction. That is not true. Okay? Friction is not dependent on the amount of surface area that comes in contact with whatever surface it's sliding on. So, just real quick, imagine we had a rectangular block. Okay? And with that rectangular block, we can set it up on one of three different sized sides. We can set it up fully tall, which would probably give us the smallest amount of surface area that would be in contact with whatever it's sitting on. We can lay it on its side, which would give us slightly more surface area. And then we can kind of lay it flat, which would give us the greatest amount of surface area for that block. That block, if we were to attempt to push that across a table or something along those lines, it would give us the exact same amount of friction, no matter which side we laid it on. And here's kind of the misconception way of thinking, the wrong way of thinking. Well, if I lay this fully flat, I have more of that object that's coming into contact with that surface. How does that not give me more friction? And the answer lies in the amount of pressure that you actually apply, or the force, per surface area. So think of it this way. If this block weighed 10 newtons, well, 10 newtons of that weight is getting distributed on a very small amount of surface area. So if you want to think about force per square inch, there's going to be a lot of force per square inch as compared to when you lay it flat. But understand, it doesn't actually change the total amount of force that's pushing down. It's just changing how it gets distributed. Okay, so when we do lay this block flat on its side like this, that gives us the greatest amount of surface area. If there's a way of measuring the amount of force per square inch or per square centimeter, however we want to measure that, it actually would be less because it's being distributed over greater surface area. So, fun little fact for you. Okay? So did you know that a sports car would have the exact same amount of traction, the exact same amount of friction with narrow tires as it does with wide tires? So long as the tread type and the tire compound, the actual what makes up that rubber, are exactly the same. So think of a vehicle, a sports car that may have wide tires, and understand that if you were to fit very narrow tires on it, so long as the tire compound is the same, exact same amount of friction. So I don't know, a Corvette or something like that. With little skinny tires, it will have the same friction. Then begs another question. Why does it come with wide tires? Why doesn't it come with narrow tires?
Because of the weight of the car.
Okay, what about the weight of the car?
Well, I mean, most cars are kind of built for heavy tires, otherwise they waste like gallons.
Okay. I hear what you're saying, but no matter what, if we take the same car, and I know that we're changing the size of the tires, let's just imagine it's the exact same weight overall. what would happen with narrow tires? What were we just talking about in the previous slide? We're applying all of that weight over a much smaller surface area. So in terms of pure friction, it doesn't change that. What does one of the major factors with it improve with a wider tire? How fast your tires wear out. Because let's be honest, if you're driving a sports car, you're probably not driving around like a grandma. Okay? So they fit them with wider tires in part to help out with tire wear, because it would be very inconvenient if in your fancy little sports car, if you had to change out your tires every 1,000 miles. Okay? Now, there is something else about a wider tire in terms of lateral grip, meaning its ability to, handle friction and not necessarily give you more friction, but the way in which it handles friction laterally speaking. But it's not going to give you any more friction as a result of the fact of it being more wide or more narrow. Okay, there's a Greek letter that I need you to become familiar with. It is the Greek letter mu. Say it with me. Mu. Mu. Not mu. It is mu. Okay? And this Greek letter mu stands for the coefficient of friction and is a measurement of how sticky two surfaces are relative to each other. For the first time all year, and we will have another one later in the year, this is a unitless quantity. It has no units. Why? It is simply a ratio of force to force. Newtons divided by newtons. So no units. This coefficient of friction, mu, is going to be very large for two very rough surfaces. If you were to have two sheets of sandpaper pressed together and you try to slide those surfaces relative to each other, you would have a very high coefficient of friction. If you were to have two very smooth surfaces pressed together, okay, and you try to slide those surfaces past each other, it's going to provide very little friction. So the coefficient of friction is going to be much smaller for smoother surfaces. Now we'll go through some samples in a little bit, and we're going to kind of get to see a little bit as to what that coefficient of friction can be. More specifically, there are two types of friction of which we are going to consider. The first of which is static friction. What does static mean?
Not moving.
Not moving. Okay? Stationary. Okay? So static friction is going to occur when two surfaces are at rest relative to each other. Meaning, you have two surfaces that are pressed together by some quantity of force, and they are not going to be sliding relative to each other. Think of a car parked on a hill. Okay, you put your car in park it on the hill. Okay? Is your car moving? Are your tires sliding relative to that road surface? No. But is there friction between your tires and the road surface? Absolutely. Okay? That is a static frictional force. Excuse me. Now, one of the things you will notice, Fs, for the force of static friction, it is a maximum value when we calculate it, meaning that we can apply up to and including that amount of frictional force, and it will still remain static. So let's just say, for mental math purposes, okay, that in a given situation that the Fs max is 100 newtons. That means that if we were to apply, let's say, 50 newtons of force, and 50 newtons would be the frictional force, would it remain static? Yeah, if the maximum is 100 and we're at 50 newtons of frictional force, it's going to remain static. If we were to apply 99 newtons of force, would it remain static?
Yes.
Yes. Think carefully about this one. If we were to apply exactly 100 newtons of force, would it remain static? Yes, it would. It is the moment that we exceed that value, 100.001 newtons, it is no longer going to remain static. It is the maximum that we can have up to and including that amount of frictional force. Now, if we calculate that at 100, another point I want to make, think about this from a free body diagram standpoint. Let's just say we have an applied force and a frictional force. FA, FFR. And those are the only two forces that we have horizontally speaking. If the maximum is 100 newtons and we apply, let's say 40 newtons, what is the frictional force? Say it again. Okay? Object is initially at rest. If we apply, the force applied is 40 newtons, what does the frictional force have to be? Its maximum is 100. It's going to be 40. Because if it is static, it's not accelerating. And just because it is a maximum value doesn't mean that is exactly what the frictional force is going to be. It just means that that's the maximum as to what it could be. So think of this from the free body diagram. If we're only pushing or pulling at 40 newtons to the right, frictional force is not going to be 100 newtons. That would mean accelerate the direction of the frictional force. That's not going to happen. Okay? So that would mean that we would have to apply a force greater than what that maximum value is going to be. Next one's a little easier than that. Kinetic friction. Okay? FK. With kinetic friction, this is something for an object that is already up and moving. It occurs when the two surfaces are already sliding relative to each other and given by that equation. One of the things that you will notice is, isn't it effectively the exact same equation? Take out subscripts. Aren't we really talking about the same equation? Yep. The frictional force, whether it's Fs max or Fk, is equal to mu, depending on whether that's static or kinetic, that will change, all times the normal force. Okay? The normal force is our measure for what's going on. Yes, friction is obviously dependent on an object's weight. But think, for example, of, we've done a couple examples of this where we had the tension force pulling at an upward angle. Does that change your normal force as per the weight? Yeah, okay. And that's an example where your weight is not equal to your normal force. We need to know what the normal force is. How much does that surface have to push back up onto the object? Because that is ultimately going to determine what is the frictional force we're going to see. Now, what's down here in the bottom, I know it's kind of a long, wordy thing, but we do need to know it. Okay? The force required to overcome static friction is greater than the force required to overcome kinetic friction. One, that's kind of due to the law of inertia. Okay? Once an object is up and moving, it is going to simply require less force for us to keep it moving because it wants to keep moving. But when something is at rest, what does it want to do? It wants to stay at rest. So it requires more force to overcome the fact that it wants to stay at rest. So even though this is a discussion about friction, if we have an object that's at rest, we have to apply more force to get it started than it does to keep it going. Okay? Now, that's kind of that in a nutshell. So anytime that we're talking about a situation, it really depends. If we're kind of along the same line, understand that static frictional forces will always be greater than kinetic frictional forces. Good. Let's do a couple quick sample problems. Okay, a 250 kilogram crate is initially moving at 3 meters per second. Find the force of friction acting on the crate to stop it if the coefficient of kinetic friction is 0.65. Step number one is to draw a free body diagram for sample A. So please, on your own, go ahead and draw a free body diagram. Nick, what's one force?
Normal.
We do have the normal force. Where does it start?
The base.
And points?
Up.
Absolutely. Okay, that would be our normal force. Okay, Nick, nominate someone else to give us another force.
Elson.
Elson, what do we get, bud? Give us another one.
Friction.
Okay, where'd you start?
On the left.
On the side?
Oh, on the bottom left.
Bottom left and pointing to the
Left.
left. Okay, I would have done that as well. I know it doesn't really go overboard with figuring it out. I would just put it in as a frictional force. Okay, even though we'll designate that as something a little more specific in a minute. Rissa? It's hard to see that though if we do it over here because we don't know the length of the arrow. It's a good question. Typically when frictional forces are drawn, at least how I have done them, think of it as the force that's being dragged behind. So that if it's going to the right, this is, I think, the best way to kind of visualize the quantity of what it is. Okay? Elson, you get to nominate someone for our last force. Anuj, thanks, bud. What do we get?
Force weight.
The weight. Okay, so center of mass pointing straight down. Good. Are there any other forces? Other than the subtle hint that I only gave you 3 spaces in your force table? No. Okay. Understand that this is already up and moving. Okay. So this is a different scenario than what it would take to get it up and going from rest. Okay, so let's go ahead, let's put those into our data table. Weight, normal force, frictional force. All right, so let's go ahead, let's take a look at our data table. What are we going to do for our weight? Does it have a component that is 0? Okay. Its x component would be 0. What about normal force? Okay, it would also have an x component of 0. Our frictional force, okay, its y component would be 0. All right. So let's go ahead and let's take a look at what do we need. What do you think that we need to go ahead and solve this? Understand that we are going to find, is this kinetic or a static friction? This is kinetic, so we're going to find Fk. Mu k times the normal force. We are given the coefficient of kinetic friction, so that part of it is easy. We do need to figure out the normal force in this problem. This is part of the reason why I provided you with a nice little table here. Okay? What do we need in this problem to figure out the normal force? We need the weight. Okay? I know that you can write it out. Let's just figure it out because it's a pretty easy calculation. Okay? Let's compute what that would be. And 2,450 is Megan's answer. Do we agree with that? Okay. It should be negative, okay, because again of the direction, but it is going to be our 2450. Is this crate accelerating vertically? No. So what does that mean? The sum of the forces has to be in this problem? 0 newtons along our y-axis at least. Okay? And then what would that make the normal force? The positive 2450. Okay? So then all we would need to do here, mu k, which is our 0.65, and remember that is a unitless quantity, multiplied by our normal force of 2450. Pluggy chuggy. And Alondra, when you have that, please let me know. 1592.5 with units of newtons, because that is going to be our force. Now, I understand that based on the free body diagram, some of you may want to say negative with that. Typically with friction, just interested in what that quantity is going to be. We'd only really have to consider the fact to be negative if we're going to use that for some sort of acceleration. Now, to give you a hint, could we do this as an acceleration problem? Find the acceleration of the crate at this point. Yeah, we would know that, okay? We could figure out what the rate of acceleration would be for our crate, at least until it gets to rest. Didn't ask you to worry about it, but I just wanted us to at least have one example of seeing how we would find that frictional force. Okay. So a 30 kilogram box, does that rest on a wooden floor where we have a static coefficient of friction of 0.50? We're going to find a couple of different things. Okay? So I'm going to draw the free body diagram for our second part of this scenario, where we're going to have a force that is applied once it's in motion to figure some things out. We know we're going to have the weight. We know we're going to have the normal force. We know we're going to have some sort of applied force, which I'm just going to put to the front side of this. And then we know we're going to have some sort of frictional force. Okay? So we can put all that good stuff into our table. So weight, normal force, applied force, and friction. Okay, for our applied and frictional forces that are parallel to our x-axis, what components for them are going to be 0? Y components. For our weight and normal force, what components are going to be 0? X's. Okay, so part A, we want to know what horizontal force is necessary just to start the box in motion. So we are going to look to find what this applied force is going to be. But if we're going to figure this out, one, is this static or kinetic friction in this part of the problem? It is static. I know that we're saying motion, but we want to know what is the quantity of force to get it into motion. That means we actually need to know what is the maximum static frictional force. Okay? So we will need to find Fs max equals mu s times the normal force. Guess what we need to find? The normal force. Okay, so we do know this is a 30 kilogram box. We can very quickly find its weight. Carly, what do we get for the weight of this box? Okay? And it would be negative again because it would be pointing down. Easy example here. What is the normal force in this problem? It would be a positive 294. We already did well, we could work our way backwards. 0 meters per second squared, 0 newtons. So that has to be a positive 294. Okay? So now if we have that, well, that's pretty easy to find that maximum static frictional force. Okay, 0.50 times our 294. So what is half of 294? We get $1.47. Now, all while this is our answer, okay? I'm okay with you just saying Fs max equals 147 newtons, but truth be told, the way that the question is asked, what horizontal force is necessary to just start the box in motion? Technically, it needs to just be a force greater than our 147 newtons. Okay? So if we only applied 140 newtons of force, is this box going to start in motion? No. If we applied 147 newtons of force, is the box going to start in motion? No. If we were to do 147.001, would it start in motion? Yes. Okay? It is just exceeding that. So more for like a short answer type question where not necessarily just doing the strict math or multiple choice or something like that. Know that that is what we have to exceed in order to get it in motion. Now, but here's the thing. Let's say we do get it up into motion. We just apply some sort of force that's greater than that. So we get it up and going. And if it's going to move at a constant speed, we want to know, if we apply a force of 91 newtons, so not at a constant speed, we want to figure out what its acceleration is going to be. In order to do that, we have to get our kinetic frictional force, mu k, times Fn. Notice how the coefficient of kinetic friction is going to be less than the static coefficient of friction. It will always be the case. And Rissa, once you get that value, let me know. Okay, 88.2, it is a force, so measured in newtons. Okay, now that is not necessarily our answer because we're asked to find the acceleration. But take a look at those two values. I know I've been kind of harping on this. Is there kinetic frictional force less than our static? Yeah, almost half of it in this case. So that is going to be less. According to our free body diagram then, if that is negative 88.2 newtons there, and we are applying 91 newtons of force, we can clearly figure out what that acceleration would be. I want you to just follow through the last two steps here to figure out what AX would be. Shouldn't be any more than about 30 seconds worth of work. Go. Paige, what'd you get for sigma Fx?
2.8 newtons.
Good. 2.8 newtons is what we should get there. Okay. And then Justin Roca, what do we get for Ax? 2.8 divided by 30 should give us
0.09.
meters per second squared. As per our free body diagram, should it accelerate to the right? Yep. We are applying a greater force than what our frictional force would be. Even though it's a very small rate of acceleration, that's what we would get. Any questions? All right, sample problem C. I'm actually not going to go through the entire problem with you, but I do want to talk about this from a free body diagram standpoint because it does bring up an interesting point. We've actually kind of have done this problem before, just not in this context. So we have an eraser that is pushed up against the wall. It must be at rest, so there is static frictional force that is here helping to hold it in place. Let's take a look at what are the forces acting on this eraser. Alex, what's one? Okay, the weight would be pulling it down. Good, that's one of our forces. Alex, what's another force? We have some sort of applied force. How would you draw it in this example?
From far side when
Absolutely. Okay, kind of pushing it into the wall. Okay, so we're going to have an applied force of some kind that is there. Okay, Michaela, what's another force acting on this eraser? Normal force. Okay, where is that going to start?
In the left.
And pointing to the, absolutely, that is the contact surface. Okay, and that is where our normal force is going to be. Okay, one last one, Matt. What is the last one that we're missing? It is the frictional force. Where is that going to be drawn? And pointing? It should be along that leftward surface. Okay. Okay, and it is going to be pointing in an upward direction. Okay? Now, sure, we could do the math to kind of support this problem, but I wanted to come back to a concept. In this problem, and this is another important one, is your normal force equal to your weight? There's a really good chance it's not. Okay? Because if you think about it, the weight that we're given, this 0.50 Newton force, actually has nothing really to do with what that normal force is going to be. But this is why the normal force is really important in our friction, because understand that it's really because of this applied force and the normal force pushing back that we have friction to begin with. We're forcing these two surfaces together, pressing them together. It's because of that that the frictional force is going to be there to hold that eraser in place.